Hello, my name is Harlow, and this is my Lab 2 on projectile motion. In this lab, I used the tracker platform to physically plot the change in position over time of a ball being thrown up into the air. The purpose of this lab is to see if this motion can be accurately tracked using a computer algorithm, or conversely, to see if there were errors in the experiment. In real life, the ball was expected to move in parabolic motion in accordance with Newton's second law in kinematics. The algorithm I used was GlowScript, which allowed me to predict the position of the ball using the average velocity and positions derived from the tracker using kinematics and Newton's second law. Furthermore, we compared a computational estimation with and without drag to see what is closer to the experiment. Inevitably, the graph of the tracker data showed a similar but slightly different motion compared to the estimated data. In terms of models, I use the kinematics equations, which are derived from Newton's second law and definitions of physics concepts. The main equation is Rf equals Ri plus Vi times delta t plus 1/2 F net over m times delta t squared, and it helps predict parabolic motion. Furthermore, we continue to use velocity and position update formula to predict future values with net force, initial velocity, and a short time interval. Velocity update formula is derived from the momentum principle, which is F equals ma, and position update formula is based on the definition of velocity, which is change in position over time. The first force we observed during this experiment is gravitational force, which on Earth is equivalent to mass times gravitational acceleration down from the system in the y direction. Gravitational acceleration is derived from the formula for gravitational force, F equals big G times m1 times m2 divided by r squared. Additionally, we showed how the ball would move with air resistance opposing gravitational force, which follows the equation F drag equals negative b times velocity squared times the unit vector of velocity. For the experiment, I used a video of a ball being thrown up and recorded the position at increasing small time intervals, setting the axes, and measuring something known in the frame. I tracked the position every 0.033 seconds. The system is the ball, and the notable surroundings are the earth and the air. For the most part, the video shows the descent of the ball and not the ascent. For coding, I wrote in all of the initial conditions by finding the initial position on tracker, which was 0.01 meters in x and negative 0.005 meters in y, and calculating average velocity from the first and third position of the ball divided by time, which was 0.066 seconds. This was 0.417 in x and 0.8063 in y. Inside of the loop were the position and velocity update formulas so that they would repeat for every value of delta t for the total time interval as tracker. Outside of the loop, I calculated drag, which increased as the velocity of the ball increases. Then, I created arrows that symbolize drag and gravitational force on the ball. In my graphs comparing the motion, the tracker data had a significantly farther displacement in the x direction in comparison to the data with drag. I believe that this occurred due to human error and that there was some mistake while tracking the data. It is possible that the mass of the paper ball being so small or the initial velocities confused the code, making the code work very differently to how it did in real life. With all these errors, we were confirmed that the equations and initial conditions were accurate, showing that this mistake was created by human error and that it couldn't be corrected at this stage. For discussion, in terms of my experiment reaching terminal velocity, I believe that none of them did. None of the models reached total terminal velocity, which is because they all show a nonlinear velocity versus time graph, as drag does not equal gravitational force in the y direction. But another experiment that could be done to create a terminal velocity is to throw it up with a lot of force, which would allow the ball to fall longer and reach a velocity big enough for drag to equal force of gravity. If the ball was thrown straight up, the time it would take for the object to reach the table would be longer than the original experiment. That is because the VI is only in that y direction instead of being multiplied by sine theta. This means that according to velocity update formula, it will take more time to reach the peak, thus more time to fall. The equations on the slide showed the time it would take to reach the peak, which you could see is significantly bigger for something that's thrown straight up in the air. To conclude, I was able to watch an object moving in parabolic motion using tracker to manually place the times, which I compared to a predicted model of the scenario, one with both drag and no drag. By comparing these two, we can see that the computational model does not accurately represent the in-person experiment for my experiment.